Hello everybody, welcome to my YouTube channel Precision Manufacturing System. I'm back with another interesting video regarding the buckling simulation of a composite panel. But in this video I will explain about the simulation, this kind of simulation by using the layup method. As you know, and if you have seen my previous video, in the previous video we actually talk about the buckling simulation of a composite panel by a stiffness matrix method. But as I promised you guys, I'm in this video I'm going to talk about defining material using layup method and see the result of buckling simulation of a composite panel. But before starting the video, I'm really grateful to subscribe to my YouTube channel and hit the like button and stick around end of this video. Your support could be a good motivation for us to create tutorial simulation video for you guys. Okay, let's get started. And actually, let's before starting the new video, let's have a review of previous simulation. But I don't want to talk about the previous simulation in details, and I will put the link of this previous simulation actually above this actually video. And if you want, you can see this video and find whatever you want from this kind of simulation, how you can model this kind of panel, because for modeling this kind of panel you should do some strategy and do some actually create some datum, and or for creating this hole we have to create some actually projection of edge, and you need to know something. Okay, after creating and modeling the panel, we use actually just a stiffness matrix for material property, and then we use buckling a step and method for doing a simulation. We actually define the equation constraint for the top edge of the panel, and then apply some constraint to bottom, side edge, and upper edge of the panel, and then apply a load, a concentrate load, to the central node of the upper edge. And then actually you can see the result. As you can see, we have the buckling simulation of composite panel. Okay, let's start the new video, actually new simulation, doing the same simulation and same procedure, but using layup method. Actually, as you know, for defining the simulating the composite material, either actually the tube or panel, we can use two different methods for defining the material property. We can use layup method or a stiffness. In previous video we talked about the stiffness method, and in this video we want to use layup method. In layup method we can actually define the thickness, or we have to define the material property in actually for in material module, and then we need to assign the created material property to our model. So let's have started the simulation. First of all, we need to define a set geometry for all part of the panel, and then we have to define the material property, but before we need to remove the previous one. Okay, so let's define it: epoxy and elasticity, and then laminal. Let me find number 90.6. Oh, excuse me, 90.6 E6, then 1.86 E6, 0.38, and for shear stress 0.93 E6, and then the last one is, excuse me, not the last one but not the least one, E6, and the last one 63 E6. Okay, and after that we have to create our layer. Actually our panel has a 16 layers, but these layers are symmetric, and just we define 8 layers and then make a pattern symmetric for the other 8 layer. So let's start it. For thickness integration rules, we choose Gauss method, and for regions, since we already defined the set, we use all set geometry. For panel and material, we use the epoxy which we had defined, and then for thickness, since the all layer has the same thickness, just write for one of them and we can use for all. But for orientation, we have different orientation and we need to write for all of them separate, actually separately. And let me find okay, 45 minus 45, 90, 0, 0, 90, minus 45, and 45. Okay, and as I said, we need to make a duplication or pattern of this layer. Choose all of them and create the pattern pairs and just symmetry. And okay, as you can see, we make a symmetric pattern for all of them. And for offset, we want to assume the shell layer is placed at the middle area of our model, and we didn't change it. Okay, and then we have to define the normal vector, and in this simulation we are going to actually assume the normal vector is located to or assigned to the external surface of our panel. So as you can see here is written brown equal to positive, so we have to flip the this color to brown. If this color is brown for you guys, it's not necessary to change it, but for my case I have to change it to brown. Now the positive direction is assigned to actually the external surface of our panel. Okay, and then we need to create the datum coordinate system, but before that we have to define a point at the center of the hole. So for that's why we have to use create a datum point between 2 points. We can use it by this method, and then create the datum coordinate system. We use rectangular, and for select the point we select the created point, and then for x-axis we choose this point, and for xy axis we choose this point. Okay, our datum coordinate system is created, and then we have to assign our material to our panel and specify the orientation and direction for each vector, and we select our model, and then we need to select and specify the coordinate system. We select the created actually coordinate system, and then as you can see the normal vector is perpendicular to the external surface, and the blue one is related to x-axis, and the yellow one is related to the y-axis as the second actually direction. And okay, it's done, and the rest of the simulation is actually the same with the previous simulation, and I don't want to speak about that because we did it in detail in our previous simulation, so it's not necessary to do it again. Just I will run the simulation and submit. Okay, it's done, and as you can see you can see the result. Maybe the result has a slightly difference between this method and the previous one, but overall the trend and actually the amount of the number of frequencies or eigenvalue maybe actually are the same, but has a little or slight differences. Okay, thank you so much for being with me until end of this video. Don't forget to subscribe to my YouTube channel and hit the like button, And if you have any question, please leave the comment for this video, or if you have any suggestion for next video, please send an email or leave the comment below this video. Thank you so much. Bye bye.